We've spent a lot of time over the past weeks talking about regression, developing tools that we can use to predict the future. And if we had a theme for our discussion of regression, it would be that of prediction. How can we take correlated variables and use those to predict an outcome? Most of the time, what we're dealing with correlated variables are variables that have been collected at a single time frame. And we're looking for the relationship between those variables. But this week, we're going to try something different. Not all data are collected at a single point in time. Sometimes we have data that are collected over a time span. And what we're going to do this week is some time traveling. We're going to look to the past to learn about the future in what we call time series analysis. I have a task for you as we start our time traveling adventure. I want you to predict for me how much time are you going to spend on your phone next week. I want you to look into the future and tell me, how much time are you going to spend looking at that screen? How are you going to make that prediction? One thing I could do is simply ask you to give me a number based upon, well, nothing, just your best guess. It turns out that we as human beings are really bad at estimating time. We're bad at estimating time intervals, like how long does it take for you to get from your house to the college campus? We tend to estimate in larger time frames. It takes, I don't know, about 5 minutes, maybe 10 minutes. That's not a very accurate answer. However, to answer this question about how much time you're going to spend on your phone next week, we have an advantage. And that is, most phones have a setting in which you can find out exactly how much time you spent on your phone last week because it is monitoring your time usage. How much time have you spent on your phone? If you have an Apple iPhone, you could go into the settings and you can look for the settings specific to time usage or screen time, and it will tell you how much time you spent on your phone yesterday and the day before, or the week before, several weeks before. Maybe there's enough data in there that we could go back several years to find out what is your pattern of usage. So when I ask you to tell me how much time you are going to spend on your phone next week, your best strategy would be to go into your phone settings and find out how much time you spent on your phone last week. And not just last week, all of those weeks that came before. In other words, your answer to the question predicting the future is going to be based on your pattern of use over time. You are going to use historic data in order to make a prediction. That's what time series analysis is about. Time travel, taking historical data and using that data, extrapolating it into the future in order to make those predictions. Time series data, a sequence of observations measured at successive, equally spaced time intervals, a sequence of observations. Remember, your phone is tracking over many, many days and weeks, months, and years. These observations are successive. They are tied to time. We're going to be interested in weekly screen time, but there are many other examples of time series data. When I was growing up at the Lake of the Ozarks, my grandfather used to get up very early in the morning. He'd get up and listen to the 6 a.m. news forecast, which at the Lake of the Ozarks also included the daily lake level. And he would write down that information in a notebook that he kept for years. Recently, I stumbled across the stack of notebooks that he had written over the many years. If you wanted to know what was the lake level at the Lake of the Ozarks on April 4 of 1988, you could find that information. He kept track of the daily lake levels. Now, maybe we're interested in something a little broader. Maybe we want to know monthly sales at our business so we can have a report for our monthly sales meeting. Or perhaps we want to track stock prices by the hour to see how they are changing and fluctuating over time. Time series data is a sequence of observations measured at successive, equally spaced time intervals. The spacing of those intervals could be every year. What has happened in the stock market over the last 100 years? Or maybe we're interested in a more fine gradation. Maybe we want to just look at what has happened over the last decade on a yearly basis. Or we could be interested in monthly sales figures as those are tracked over the last year. Or it could be by the quarter or the month or the week or the day or the hour, the minute, the second, even the millisecond if we are interested in data that finely tuned. It does not matter what the intervals are as long as they are equally spaced. Time series data are measured at sequential, equally spaced time intervals. The choice of the interval is going to be dependent upon what you want to measure, but the choice that you make is also going to affect the patterns that you can observe. If we are measuring by the second or the millisecond, we will have very fine gradations, which gives us a lot of information, but it also gives us a lot of noise in our data. On the other hand, if we want to look on a broader scale, looking at monthly or yearly measurements, it's going to coarsen out our measurements, which will smooth out the fluctuations. However, if we get too coarse in our time interval choices, we might be hiding patterns that exist within the data. So it will be important that we choose an interval that is best suited for the data that we have. Forecasting is about using historical data to make predictions about future events. So for example, we want to predict how many hours you are going to spend on your phone next week. In order to answer that information, we go into your phone and we gather information from the last 3 months. So now we have 12 data points collected weekly over the last 12 weeks. We're going to use the data from the last 12 weeks to forecast or to predict how much time you're going to spend on your phone in the next time period, week 13. How are we able to make these predictions? Well, the best predictor of future behavior is past behavior. So the best predictor of how much time you're going to spend on your phone next week is how much time you've spent on your phone last week. Unless we have more data, maybe not just last week, but a larger pattern of data, maybe going back 12 weeks. The more data that we have, the better we are able to identify those patterns. The time series analysis is going to use historical patterns to predict trends of future behavior. Do you use your phone more on weekends? That's called seasonality. Has your usage gradually increased over the months? That's a trend. Did your usage drop off suddenly during finals week? That's an outlier. Did you start a new job that does not allow phones during work? That could be a shift in your pattern. These are examples of the patterns and trends that we're going to find within our time series data. But it's important to note the difference between time series analysis and causal analysis. With time series analysis, we are simply basing our predictions on time values. I am predicting week 13 based on the data from weeks 1 through 12. If I look back, I might be able to explain why a change occurred. In this week, there was a big drop, and that was because that was midterms, and I spent a lot more time studying, and that's why there was a drop in my phone usage that week. And then it bounced back to a more typical number the following week. But without looking at any of those changes, looking only at the data, I can make a prediction based upon that historic data. Causal analysis would be using other elements of the historic data, like your class schedule for the semester, or social events in which you're more or less likely to spend time on your phone, or the latest gaming releases when we know that the new Car Theft Auto is coming out and you're going to be up all night playing that game. We're going to predict a big increase as the result of that change. That's causal analysis because I'm using information other than time. Time series analysis is limited only to time as a predictor. The first step for understanding time series data is to get a good, clear picture of them. We're going to visualize our time series patterns using a time series plot. Now, a time series plot is actually a scatter plot, at least if we create it in Excel. It'll use the same settings and functions as if we were creating a scatter plot, but it's a special kind of scatter plot. This is a scatter plot of data that is occurring over time. So what we're going to do is plot time and the occurrences, like number of hours spent on your phone in that given week, on the two axes. And then we're going to connect those data points with straight lines. We're going to plot time on the x-axis. So we can see here weeks 1 through 12. The event, the thing that we are using as our dependent variable, is going to go on the y-axis. Those are the time series values. And in this case, it's number of hours spent on your phone during the last week. You can see the straight lines that are connecting these dots. And because they are being measured across this 1 to 12 time week span, we see them nicely separated. And that allows us to see the patterns or maybe the trends that are occurring with our data points. Anytime you look at a time series graph or a time series plot, you're going to see some kind of pattern revealed in that plot. What are the potential patterns that you could see? What should you be looking for? In this example, we are seeing something which is called a horizontal pattern. In a horizontal pattern, the data are fluctuating around a constant mean. Let's say that we have a machine that is making 50 millimeter ball bearings. And for quality control, we measure a random sample of those ball bearings every a few hours. At the beginning of the shift, we take a measurement, make sure that our machine is still dialed in correctly and making ball bearings at exactly that 50 millimeter, or certainly within spec for our 50 millimeter range. And then we measure again at lunchtime and then maybe again at the end of the shift. So we're measuring sequentially over time. What we should see is that sometimes there will be a slight variation over or a slight variation under, but it is going to be very consistent. If we average it all out, it's going to stay at that 50 millimeter range. Or maybe we have a business that has reached market saturation. Maybe it's a car wash at a part of town where the market is saturated, which means that some days there will be more cars coming through, some days there will be fewer cars coming through. But because of the stability that we see, we can say that there will be an average number of cars that pass through per day, and that average is going to be a pretty good estimate. The horizontal nature of this pattern is called stationarity. It's when the statistical properties like the mean and the standard deviation, the autocorrelation structure, are remaining constant over time. If you grew up in a small town, you might have experienced this phenomenon of stationarity, where over the years, babies were born, they grew up, married as young people, had children of their own, and then eventually grew older and aged, and now they're buried on the cemetery on the hillside. Every year, babies were born. Every year, people died. But the population stayed stable. Unless something happened to change that pattern. World War I occurs, and all of the young men in this small town are called off to war. And now we see a change in the population. Or maybe economic changes occur in the nation that cause there to be lower levels of population in this small town. Stationarity can also be accompanied by shifts. This is sometimes called the new normal. So for instance, you start a job at a company that does not allow you to use your personal phones. Maybe it's some kind of governmental agency and they're very concerned about security. We can't just have you twittering away on your personal cell phone about state secrets. And so they tell you, don't use your personal phone. You have to put that away. And since you've started this new job, we've seen a shift. We've seen a drop in how much time you spend on your phone on a given day. That shift occurred because of some external change. Now you're at a new normal. Maybe the mean has changed. You'll still be fluctuating around a mean, just a different mean than what you used to have. A linear trend pattern occurs when we have a gradual direction of movement over time. Maybe we're looking at the demand for electricity by year, and we see a gradual increase along our time series plot. Maybe we're looking at fitness gains. You have been improving your fitness over time, and as we track this over many, many weeks, we see an increase in how physically fit you are. These trends, changes over time, which could go up or could go down, are often affected by shifts in population, in changes in the market, or in consumer preferences. Technological advancement is another very common reason why a trend might change. The introduction of new technology, like cell phones, changes the way that people behave. So we see a trend that occurs over time. Not all trends are linear. Some are non-linear. In fact, my example with cell phones would probably follow more of an exponential trend, an increase at a constant percentage rate. In a similar vein, we have Moore's law of computing, which states that the computing power of chips will increase or double at a certain rate over time. Or we could remember the COVID-19 pandemic, which occurred back in 2019, 2020, and so forth. One person infects 3 people, and each of those 3 infect 3 more people, and then those infect 3 more. And what we're seeing is not a linear growth, but an exponential growth. With more and more people infecting more and more people, we're seeing a dramatic upswing. That's a nonlinear pattern. Now, we can analyze nonlinear trends as well as linear trends, but we're going to use a different technique for doing that. We're going to be using a linear progression, a linear prediction, and we're also going to look at a quadratic prediction. We'll do both of those here in a little bit. The seasonal pattern is where you have fluctuations that occur at fixed intervals. And because of the nature of the seasonal patterns, those changes become very predictable. Like if I ask you to predict the sales of turkey, I'm going to guess that turkey sales are not consistent over the course of a year. Toward the holidays, especially toward Thanksgiving, sales of turkey is going to go way up. And I suspect you'd probably see a drop in turkey sales in the early spring. There are changes which are predictable. The sales of ice melt, the substance that you sprinkle on a surface that is covered with ice to help melt the ice and keep it from being too slippery. Ice melt sales increase in the winter and they decrease in the summer. There's a seasonality to the pattern of those sales. So there are 2 important things I need to clarify about seasonality. The first would be that these seasonal patterns need to occur in less than 1 year. They can occur much more rapidly than that. There's patterns that emerge over a semester in an academic setting. There are patterns that could emerge over the course of a single day. Your coffee consumption, for instance. But the patterns have to be less than a year. And the other thing I should clarify about seasonality is it doesn't necessarily have to do with the 4 seasons, spring, summer, winter, fall. Or depending where you live in the world, maybe the 3 seasons or the 2 seasons. It's not about the seasons, although weather patterns could certainly affect sales. It is something that is predictable and recurring in a pattern that we are able to observe over time. This is called the trend and seasonal pattern, or a mixed pattern, a combined pattern. It's showing both a directional movement, there's that upward slope of the trend, along with these predictable, regular seasonal fluctuations. If we look at airline travel over time, airline travel will fluctuate over the course of the year, but there's an overall increase in growth. Another example would be an academic YouTube channel. Let's say that there was a professor who started a YouTube channel 15 years ago. That person might observe seasonal changes that occur over the course of a semester. So for instance, if you had a YouTube channel about, statistics and research, you might notice there are more views during certain times of the year, specifically related to the academic calendar, than there are at other times. So for instance, this time of year, as we're getting close to finals week, we might have a fairly high number of views on that channel. But guess what's going to happen right after finals week here in the spring? You're going to see a big drop in the number of views or the number of subscribers. Now that drop will be large, but not as large as one that we're going to see in the fall. It will probably increase as we go into the summer, as the summer semester starts up. It won't be as big an increase as we would see in the spring and the fall, but there's a certain increase until we get to finals week of summer calendar, and then there'll be another drop. But when we get to late August, early September, there's going to be this huge increase in views and subscribers as more students are going back to college and they're interested in learning about statistics from someone who's able to explain statistics and research and the use of statistical software in a very clear and understandable pattern. So that's the seasonality of this YouTube channel, but there's also a trend. You see, over the last 15 years, more and more students have found this channel. And so when we look at the pattern, we also see an upward trend in number of views or number of subscribers. The number of views last August is going to be different than the number of views this coming August. And some of that increase is going to be due to the change in the seasonality. In other words, we're heading into the fall semester. More students are watching the channel. But then there's also a trend that has occurred where there are more subscribers, and now we're going to see an increase due to the trend. In order to tease out what is due to what in this model, we're going to have to separate the trend from the seasonality. And that is called time series decomposition. Separating the trend from the seasonal components so we can see what elements of the increase are due to trend versus seasonality. We separate those, analyze them separately, and ultimately those will be brought back together for making a final prediction. Now, this is a pattern that we are not going to spend much time talking about, but it is very important that you know what it is. The cyclical pattern has these alternating increases and decreases that occur without fixed periodicity. Now, the word periodicity is referring to this time that it takes for a pattern to repeat. If we're talking about coffee consumption across daytime, coffee consumption, I know certainly for me, it's going to be the highest in the morning, and then it's going to decrease, certainly done by noon. It'll stay low until the next morning, in which case it's going to increase again. The periodicity is one day. I can tell you when that pattern is going to repeat. But there are patterns that repeat at intervals that can't be predicted. They're probably going to go on for longer than 1 year, and they're going to be patterns that just don't tell us very much, or at least don't tell us what we would need to know in order to make predictions about them. So let's look at this example where I'm using the Dow Jones Industrial Average over roughly the last 30 years. What we're seeing is a big run up in the 1990s until we get to around 2001, and then there was a change that occurred. The attacks on the World Trade Center and the Pentagon on 9/11/2001. There was a decrease in the Dow Jones, which led to a recession. That external change, the 9/11 attacks, was nothing that could be predicted. Therefore, it was not possible to look at earlier trend patterns and predict what was going to happen next. So if we continue looking at the pattern, we see this dip between 2000 and 2005, which began to recover until we got to around 2008. And then there was another crash. And that crash lasted for a lot longer period of time. That recession went into the next political administration. And then finally, about 2 years, 2.5 years in, you start to see that growth increase. Now we see a strong, steady growth from the end of that 2008 recession all the way through about 2020. And then something else happens external, the COVID crisis. And in 2020, everything shut down, and the response to COVID was being handled in a way that also contributed to another recession. So we see that big drop. And after we got COVID under control, we got the vaccines, we started to see a resurgence and a restoration. And now we see this increase that occurred, and then another drop, and then another increase. Point is, it's not possible to predict what's going to happen simply using these time series values. So when we have a cyclical pattern, it's going to go on for more than 1 year, and it's not going to be easily predictable. Therefore, it's not something that we're going to spend a lot of time with in this course, because our lessons here are really about how to use time series values for prediction.